In 1868, a Dutch physiologist called Franciscus Donders had an idea that sounds obvious now, but genuinely it sounded radical back then. He thought that he could time a thought. His reasoning went like this: ask somebody to press a button the moment a light comes on, and measure how long they take. Then ask them to press one button for a red light and a different button for a green light, and measure that. The second task takes longer, obviously. Subtract one from the other, and what is left over is the time it took them to decide. People at the time thought mental events were outside the reach of measurement. Donders handed them a stopwatch and a subtraction. That number, it's called reaction time, is still everywhere in cognitive science and neuroscience fields. It is in cognitive psychology, in clinical assessments, in half the neuroimaging experiments running today, and it has a shape, one row per trial, with columns saying which condition it was, how long they took, and whether they got it right or not, which is a table, and that is today the other half of your data. Last session, we handled signals, long ordered runs of numbers where position means time. But no experiment is only a signal. Around every recording there is a second kind of data. Which trial this was, which condition, which participant, how old they were, whether they were awake, whether the trial got rejected for motion. Signals are arrays. That other stuff is a table. And in Python, a table is a pandas DataFrame. Another cool thing, why we're discussing it in Python, like the only original question that the title says for every session, Python for Neuroscience, Introduction. In order to do all this that we're doing right now, all the way from importing the data we have, dealing with the analysis, with the phenotypes, and the metadata that we have, you have to use numerous other tools if you're not using Python. You have to use Excel or similar tools for the exact thing that we're doing right now in this session. You have to pay for an outside application. Or if you're going to use any other tool for signal analysis, for example MATLAB, you have to pay for the subscription for the application license, which is actually a lot. So we are handling every corner of dealing with research in neuroscience, all done in Python for free, well maintained and published methods. So let's continue. As I mentioned, signals are arrays. The other stuff is a table. In Python, a table is a pandas data frame. You need both. An fMRI scan, like what I did for my master's degree thesis, you need both. Without the events file telling you when things happened is just a very expensive movie of a head. This is not a joke. Incidentally, there is a whole standard for this. It is called BIDS or BIDS, the Brain Imaging Data Structure. And it says your imaging data ships alongside plain text tables listing when each event happened and when it went, actually what it was. When you download an open dataset in session 11, which we will deal with it like hands-on, that structure is what you will find. Okay, building a table. So let's simulate a small experiment. 60 trials, 2 conditions. In the attend condition, the participant knows roughly where the target will be. In the ignore condition, they do not. I have built in the effect you would expect, like attended trials come out faster and more accurate. It's observable right here. Okay, attend and ignore. Then we have the size, which we have put as 60, an integer, constant number, and this orangey thing we will go through. That expectation you have is not arbitrary. Michael Posner ran essentially this experiment in 1980. He gave people a cue about where to look, and valid cues by you a few tens of milliseconds faster. It is one of the most reproduced findings in cognitive psychology. The usual way to build a data frame is from a dictionary, which we were introduced in a couple of sessions before this. And you know already about the dictionaries from session 4. Each key becomes a column name, and value becomes the column itself. Let's run the cell and see what's happening. I usually have to run the first cell before I start recording, so I wouldn't waste your time on waiting until the runtime comes online, but bear with me. Okay. And this beautiful little data frame, or table. The usual way, yes, as I mentioned. So basically, data frame is built from a dictionary. Let's look at the head, or this actually basic this head here. Shows you the 5 rows. There is tail also, which you can use, like the exact same command, trials.tail, which gives you the last 5. And if you're being careful, sample, which allows you random rows, is much better at catching problems hiding in the middle of the file actually. So let's run so we get the tail as well, but if you do it 2, you have to actually put a print, so you would get 2 at the same time. Since this is hands-on and I have to make it short, let's run it quickly to get both of them. Okay, it gets out of style because we have printed it, but it's generally doable. Just for the idea. Okay, 57, 55 to 59, the last 60 trials, and 0 to 4. And remember, Python started indexing from 0 for the head for the first 5, tail for the last. Okay. This being said, okay, notice the shape of this. One row is one trial. Let's run it again and look at it. One row is one trial. The one column is one thing you actually measured. For example, the condition, the reaction time on like milliseconds. Keep your tables in that shape, and every tool in this ecosystem will cooperate with you. This very statement I said, this ecosystem and the tools cooperating, you'll see what I mean. Okay, right here. Let's run this box, see what happens. Okay, shape from trials, the dataset, the data frame we have. That shape tells you rows and columns, like what we have. 4 of them, and 60 rows and 4 columns in this dataset. And describe that columns that trials that describe right here gives you count, mean, standard deviation, and quartiles for every numeric column at once. Imagine all we did was, of course, we had to synthesize the dataset here, but imagine if you have the dataset already. All you do is import it to Python using pandas, which we will go through. So this is, generally speaking, we're just discussing pandas in its synthesized data, just to understand what's happening here. But if you do that, like that would took like 2 to 3 lines of code, and running like this is basically just 2 words, like trials, which is our dataset, dot describe is what we write with 2 parentheses, gives us the measurements that is most typically reported in almost every scientific paper in this field. What would that make? Like 4 or 5 lines of code, all free, well maintained and published. That is the strength of Python. So, run this on every table you did not create yourself. It is the fastest way to find the impossible things. A reaction time of -40, an accuracy of 1.3, 300 trials in a dataset that should have 240. That is not being fussy. Those errors are actually extremely common, and they are silent actually. So, let's go getting at your data. One column in square brackets that gives you a series, which is basically a numpy array, okay, in this format. Gives you a numpy array with labels attached, and all the methods from the last session work on it. Let's run it and see what happens. Okay, trials in the dataset inside the brackets, the square brackets, rt underscore ms, which is the reaction time, right here, the column name, which we introduced right here when we were building it. Here we're building the pandas, the data frame. rt underline ms is the column name. If you give it to the column name, it will return all the values in that column, every row values of that column, and yeah, in form of an array, a numpy array. And all the methods we've had based on that all work simultaneously on that exactly thing. Okay, like what? Like dot mean. So you can actually get the mean of every value in the reaction time column or RT column easily. One line of code. Amazing, isn't it? Now for the conditions. How many values we have for the conditions? If we give it, it will actually tag it and return it. 33 for ignore and 27 for attend. Beautiful. So, let's run this. Value counts is the other one I basically use, so we've had that. Filtering rows works by writing the condition inside the brackets, okay? Like we want to, like this. Trials is our data set, we want to start filtering it. We write a bracket, then we put our conditions inside it, and this way it will only report back to us the values that we have put the conditions for. For example, in trials data frame, read it like this: in trials data frame, like the whole data set. For the trials, which row based on the reaction times or RT is less than 400, and trials that are correct. So this will only report back to us the values that both of those conditions are true. Reaction times are under 400 milliseconds and they are tagged as correct. You can see it. These 8 trials were both fast and correct, basically. That's what we meant. So, yeah. Read the line out loud. Give me the trials where the reaction time is under 400 and responses were correct. Yeah, basically that's all. Okay, let's go to groupby. The reason people use pandas most often. This is beautiful. Here is the thing that makes this library worth learning. Split the table by condition. Apply a calculation to each piece. Combine the answers into one small table. The pattern covers an enormous fraction of what anybody does with experimental data, and it is in one simple line. Recreated the dataset, calculated what we wanted from it, and reported back as summary. And there is your result. Mean reaction time per condition. I swear, like if you were in charge of gathering the data, actually reporting this would be a major part of your basic analysis. The spread, the accuracy, and how many trials went into each actually. So, attended trials came up roughly 70 milliseconds faster and considerably more accurate, which is what I built into the simulation. So this is really tells us that the pipeline works because I intended it to be this way. That is the correct way to use fake data, because that way you can actually check to see if the data that you have intentionally made in some way, what you're doing, your analysis does get that right or not. So this way you learn. That's the basic reality check. Okay, the favorite part of mine, the visualizations. Let's first run it and see what happens. Okay, these are the same numbers just drawn. Bars are the group means, attended and ignored. The whiskers, these jiggly things, are the standard error. Do not skip the second part. The standard error is the standard deviation divided by square root of your sample size. And it says like basically how well you have pinned down the mean rather than how spread out your data is. Collect more trials and it shrinks. So that's based on experience. You know, numerous previous research on this field. The standard deviation does not. So basically, a bar chart with no error bars tell you almost nothing. 2 bars at different heights is not a finding. It is a picture of 2 averages. And averages of noisy things differ every time you run anything. Session 9 is where we do this properly and actually test it. So tune in. Bringing the signal back. You remember this. You must remember this. Please remember this. One more thing, because I do not want you thinking signals and tables live in separate worlds, because they do not. Here's our toy signal from last session, 20 seconds of it. I am cutting it into 20 segments, and for each segment computing a mean, a spread, and a peak. Then I put 1 row per segment into a DataFrame. Okay, let's run this too, see what happens. Okay, and look at what just happened. That's a signal. Now it's a table. Yeah, there are not 2 entities, remember. That step is essentially in every analysis in this field. You reduce long recording to a handful of numbers per trial, and from that point on, everything you do is a table work. Statistics, plotting, comparing groups, all of it. Signals in, tables out. That is the shape of the job. So that's not the end of it. If I get the chance to discuss other aspects of Python for neuroscience, for example, machine learning and neural networks, hopefully in the future after this series ends, you will see that the mean comparison is not the only way to actually study in this field or any other field actually regarding this. So basically, data frames for anything with rows and columns described to check what you have been handed. Filtering to select, and group by for splitting and summarizing is what we've been discussing all this session. The exercise at the bottom, this beautiful, try it yourself, is a good one actually. Group trials by whether the answer was correct and stuff. By condition, which we actually did, and look at the reaction time, see what happens. This is very good if you manage to actually mess around and run these cells for yourself and see what happens. This is the cornerstone of any mean analysis in basically science, because this is not just this is the methodology. This is like real science behind that. People are often like slower on the trial right after they make a mistake, which is called post-error slowing, and has been studied since the 1960s. Numerous research behind it. Whether errors themselves are faster or slower than correct responses depends heavily on the task, and people argue about it. Your simulation data will not settle that debate, but you now have the tool to ask the question. Like, that is the whole point. Next session is plotting. We have been making figures since session 2 without me explaining anything about it, but now we stop. We discuss Matplotlib and every type of plots that we have drawn right until this session to actually for you to be able to do it yourself. Notebooks and data are all freely available on GitHub. I have put the link in the comment section, and I hope to see you in session 7. Please enjoy. Bye bye.